There are few people on Earth more qualified to speak on mankind's mission to Mars than tonight's expert. Ladies and gentlemen, it is my great honor to introduce to you our guest, Dr. Pascal Lee.
Thank you so much for coming. Surely you have something better to do, but I really appreciate your presence. It really is incredible. So before I even begin, I just am completely wowed by how beautiful this library is. And the architecture and just the coziness of the library, it's wonderful. So I don't have a library like this where I live, which is just in Santa Clara. It's nice, but it's not like this one. So it's a real privilege to be here. Thank you. Tonight, I'm going to talk to you about something that might seem arcane to people who are really busy with the important things in life. But in the big picture, maybe this is actually one of the more optimistic and hopeful things we should really be doing with our lives. So I'm going to talk to you about this idea of going to Mars and where we stand on it. So the talk is titled Earth to Mars, Steps Towards the First Human Mission to the Red Planet. I'll tell you more stories down the road. I have two science education stories I like to tell just before I jump into this talk. They're just stories that emphasize the importance of science education. So one of them is simple. I was on this flight to the East Coast. We're flying over Arizona. The captain comes on the intercom and says, "Ladies and gentlemen, right next to I-40 there, down there, you can see Meteor Crater." So everybody leans over to the left, looks at Meteor Crater. And this person next to me says, "Oh, wow, it almost hit the freeway." It was not dumb. It just reflected ignorance of the fact that meteorite impacts are recording a longer history than that, and so anyway, but it was not illogical. The second story I'll tell you later if I have time. Okay, so let's move on. Okay. So, Houston, we have a problem. Okay. All right, so the talk is organized this way. It's what, why, how, when, and who of a human mission to Mars. Okay, so let's start with what is a human mission to Mars? Okay. All right. I need to be heard louder. Okay? Is this a little bit better? All right. So here we are. This is planet Earth and our moon to scale. This is roughly how small the moon is. It's actually farther from the Earth than portrayed in this picture, but in terms of their relative sizes, that's how small our moon is. And most people imagine the moon to be slightly bigger than that when they look at it on the horizon, but it's just about this. All of our concerns, all of our businesses, all our pending lawsuits, medical malpractices, all the things we do, the wars, the plays, happen on this little ball in space. And one of the nice things about being an astronomer or wanting to go to Mars is that you really put all these things in perspective. And one of the things you should realize is that, of course, we're going around the sun. And every second that goes by, we've traveled 30 kilometers on this path that takes us around the sun. We go one full circle around the sun, of course, once every 365.25 days, which is why we have a leap year every 4 years, an extra day to catch up. But here we are in motion through space, hurtling through space. And the sun itself, of course, is going around the center of the galaxy. And it's traveling around the galaxy. And it goes one full circle around the galaxy once every 250 million years or so. Okay. So we're running into things within the solar system. There are asteroids that are still flying around, comets that are coming from farther out. It's a happening place. And so, meanwhile, we're so busy with all our day-to-day things that astronomy tends to be relegated to the things that are somehow ethereal or theoretical. But the truth is, this is the reality, the physical reality of what's happening. And all of our concerns in general tend to be really secondary to this brutal reality of us traveling through space. So the Earth-Moon distance, in reality, is shown here. That's the Earth and the Moon, that little gray bleb on the right, to scale. The distance between the Earth and the Moon is about 0.4 million kilometers. It takes you about 3 days with current rockets, like the Saturn V of the 60s, to travel to the Moon. And once you get to the Moon, you can stay there or come back immediately. You can go to the Moon and back to the Earth, come back to the Earth within the week. You leave on Monday, you're back Sunday night. Okay? So the Moon is really our neighborhood, and yet only a dozen people have walked on the Moon. And so far, since the Apollo program, since the last astronauts who walked on the Moon, Gene Cernan and Jack Schmitt, on Apollo 17, that was in December of 1972, nobody has ventured beyond 1 pixel of this image of the Earth. Okay? So low Earth orbit, the space station, the space shuttle, Salyut, Mir, all of this exciting stuff is very close to the Earth. It's within 1 pixel of that image of the Earth to the left. Okay? And so going to the Moon, what you have to realize was really an incredible feat. And to me, when I hear that people are questioning whether we actually went to the Moon, there are people who are, revisionists and are really wondering if it wasn't just a hoax. That makes me think of 2 things. One, again, science education. You're never done with teaching science and reminding people of the things that we have actually done. But the other thing is that it's almost the best compliment you could possibly pay an engineer when 40 years after what they've done, there are still people who are in disbelief of that achievement. Okay, that is something. It also tells you that we're far behind in terms of where we could be in space. We've sort of been milling around and could be farther. So where could we go? Well, here's the Earth in a sort of shrunken version of the solar system. The planets are shown to scale in terms of their sizes, but not in terms of their distances. The Earth and the Moon, you can see them there. Venus is the closest planet, actually, technically. It comes closest to the Earth. But it's towards the sun, and that's bad news. You have a super greenhouse effect going on Venus. Temperatures at the surface are so high, they're close to 495 degrees centigrade. That's the melting temperature, that's above the melting temperature of lead, okay? That's a temperature where mercury in your thermometer would not even be a liquid metal, it would be a vapor, okay? So Venus is a nasty place. There's no liquid water at the surface. The clouds have layers of sulfuric acid, literally sulfuric acid, okay? So it's a good impersonation of hell. Mars, on the other hand, is the next planet out. It's sort of the cooler place. And if you were an extraterrestrial civilization venturing into the solar system for the first time, you would give no thought or even glance at Mars. You would just go straight to the Earth, I think, because the Earth is the happening place. It's the oasis. It's location, location, location. We are close to the sun. Liquid water is available in abundance. Life is teeming. Okay? And Mars is this dry little cold world that is of interest to us because we are on the Earth and it's the next planet out. But in the big picture of the cosmos, Mars is a run-of-the-mill planet. Now, let's talk about distances. You saw the distance between the Earth and the Moon? Okay. So the Earth is going around the sun in this bottom view along the blue-colored orbit. Mars travels around the sun in a wider loop. It takes Mars 687 days to go 1 full circle around the sun. And the Earth is traveling faster than Mars. So not only is the path the Earth has to follow shorter, but the Earth is physically traveling faster around the sun. So the Earth is constantly overtaking Mars. And so this happens every 26 months. And when the Earth and Mars are their closest, the distance falls to about 55 million kilometers. But when the Earth and Mars are on opposite sides of the sun, that's when the Earth-Mars distance is 400 million kilometers. And that means that Mars, when it's at its farthest from the Earth, is 1,000 times farther than the Moon. Okay. So going to Mars is not just, hey, it's the next step in space. It's really the next giant leap for us. Okay. And it's not an easy leap. So how long would it take? Well, here's a scenario from my children's book. You'll see a few more of those. The sun in the middle there. If you depart from the Earth, where it says start here, it will take you about 6 months using conventional rockets, nuclear actually, ideally here, to get to Mars. So you follow that yellow trajectory. And you loop around the sun because you take advantage of the velocity that the Earth already has and Mars has to travel around the sun. And then once you get to Mars, you have to sort of commit to stay on Mars because the Earth is not where you want it to be to come back immediately. So you need to stay on Mars 18 months, and then it's another 6 months for you to come back to the Earth. Okay, so all in all, you're gone 6 months in deep space, plus 18 months on Mars, plus 6 months in deep space, 30 months. That's 900 days. That's 2.5 years. Okay, so before I go further, let me do a quick non-scientific, meaningless poll. Who here would even consider leaving the Earth for 2.5 years and going to Mars? Okay. All right. So this slide is a little more detail. It's for when you're at a cocktail reception and you want to impress somebody, or you run into somebody who's going to Mars. So the scenario I just showed you on the left is what's on the left. It's 6 months there, 6 months out, 18 months on Mars. You come back 6 months, 905 days. The advantage of conjunction class missions on the left, the one I showed you earlier too, okay, same thing, is that of all that time that you're gone from the Earth, the 905 days, most of that time you spend on Mars. You spend 1 year in deep space, 6 months and 6 months, but you spend 1.5 years on Mars. In the opposition class mission, the total duration of the mission is only 600 odd days. Okay, so the total duration of the mission is less, but you end up spending most of your time in deep space. Take a departure from the Earth here in 2031. Okay, it'll take you about 313 days, almost a year to get to Mars. And then you stay about 40 days on Mars. And then you sort of catch the fly back to Earth express, so to speak. You dive towards the inner solar system. You even cross the orbit of the Earth. You cross the orbit of Venus. Okay, you loop around the sun, and you catch up with the Earth on its backside, so to speak, to get back to the Earth. Venus may or may not be there when you cross its orbit. If it's there, these missions are called Venus flyby missions. Okay. But again, you're spending about a year in deep space doing this loop, but your total time gone from the Earth is only 600 odd days. Okay. So my guess is that for early missions, we might go opposition class, but for later missions, when we have an infrastructure on Mars, we can afford to spend time on Mars, we'll go conjunction class. Okay. So you can ask your friend at the cocktail reception, are you traveling conjunction class or opposition class? All right, so where do we stand in terms of our experience? Well, so far, this is the guy who spent the most time in space on a single flight. He actually went on 2 space flights, but the record-breaking flight he went on lasted 437 days and 18 hours, okay? So 1.2 years is the current record of a human being spending time in space on a single space flight. He was a Soviet cosmonaut. He's a medical doctor. He's a physician, and he's just fine. All right. Now, also, the current person who has the longest cumulative time spent in space over the course of 5 missions is 2.4 years. So this guy spent 2.4 years of his life in space, and He just broke the record on June 28th, 2015, okay? And there you have it. So we're getting to that ballpark of mission durations that will be commensurate with what a mission to Mars will take. And then you have these experiments that we're doing on the ground. This is an experiment run by the European Space Agency with the Russians. They locked up 6 volunteers, all guys, in this facility in a basement in Moscow. So it was called Mars 500. It actually lasted 520 days. The crew was put through the different stages of a mission to Mars. The deep space phase, where they were essentially cooped up in a module. Then they were allowed to land on Mars and were given a sandbox to walk out on, wearing a spacesuit, okay? And then they had to go back into this vessel, pressure vessel, to fly back to the Earth, and that whole thing lasted 520 days, okay? So I have mixed feelings about these experiments. They can be useful if you are sort of really focusing on specific things, but the general lessons you learn are things that we're already familiar with. Number 1, don't talk politics, okay? Number 2, don't talk religion, okay? The big lesson basically is that if you can survive 520 days in a basement in Moscow, you're ready for Mars, okay? So, but seriously, these experiments are useful, although they have some limits. The main limit that I see is that throughout this whole journey, even though the crew is put through emergencies and fire alarms and bells and whistles, they're not really faced with a real danger, okay? With real life-threatening danger. And when you're not faced with real life-threatening dangers, your behavior as a crew member is different. Because, hey, next thing you know, your commander is making some decision that you're vehemently against. You think that's going to kill everybody. All right, so we talked about the duration, the distance. Let's talk about sizes and gravity. This is the Earth, Mars, and the Moon and Mars to scale. On Earth, you're on a big ball, so you feel a strong gravity. That's 1 g. On the Moon, gravity is 6 times less, so it's 0.17 g. This is why, if you're hopping around on the Moon, you feel so much lighter. If you say weigh 100 pounds on the Earth, if you weigh 100 pounds on the Earth, well, first of all, consider yourself lucky. But second, on the Moon, you would feel that you weigh only 17 pounds. Okay? So you would hop around, with leisure. Now, on Mars, the gravity is 0.38 g, so it's 38% of Earth's gravity. If you weigh 100 pounds on Earth, you would feel that you weigh only 38 pounds on Mars. Okay? All right. So you can jump 2.6 times higher on Mars. If you were to play basketball on Mars, to keep the game fair, you'd have to raise the hoop 2.6 times. And a slam dunk would be spectacular. Okay. All right. So here's what the planet is like. It looks friendly, welcoming. This is a Hubble Space Telescope view of Mars. It's a beautiful planet. You can see its atmosphere. It has polar caps. There's no sign of oceans. These dark areas are just mostly volcanic rocks that are very dark, like the basalts of Hawaii. The brighter areas are covered mostly in lighter colored sand and dust. So from this perspective, it looks like a nice place. But here's the reality check. On the left, you have the list of good things about Mars when it comes to human mission. On the right, you have the list of things that will kill you. Okay, and I've listed them from top to bottom in chronological order of cruel and unusual death. Okay. So first of all, let's say you are exposed to the Martian surface environment without a spacesuit. Okay, you're exposed to the low atmospheric pressure on Mars. The atmospheric pressure on Mars is close to 100 times less than what it is on the Earth. It's what you have on Earth at an altitude of about 125,000 feet. 36 kilometers. So the other day when Felix Baumgartner jumped from the stratosphere to parachute down to New Mexico, he launched himself from the gondola at about 125,000 feet. He was at Martian atmospheric pressure. This is why he had to wear a spacesuit, essentially, a pressure suit to keep him alive. All right. So if you were exposed, as we are now, to the Martian environment abruptly, that's the first thing that would kill you, the low pressure. Okay, all the gases right now that are dissolved in your bloodstream, the oxygen that you just breathed in along with the nitrogen, with the low pressure outside, these gases would not be confined to your blood, they would bubble up. Okay? And so even at the cold temperatures of Mars, your blood would boil. Your blood in your veins, in your vessels, in your arteries, they would just boil. They would bubble up. You would fizz to death. Okay? So that's what I mean by cruel and unusual. Now, it's pretty much instantaneous, although probably not fast enough if it's really happening to you. Okay. The second thing that will kill you if the first thing did not, and this is now very academic because you're dead, is the fact that you cannot breathe the Martian atmosphere. It's made of carbon dioxide. Okay. There's no free oxygen, O2, like we have in our atmosphere. It's made of CO2, which is the gas that you exhale. And that's actually a toxic gas for you. If you are confined, cooped up in an environment where you can only breathe CO2, you would die. So the Martian atmosphere is toxic, and you cannot survive by breathing it. The third thing that will kill you quickly, but not that quickly because there's some thermal inertia in your body, is the fact that the temperatures on Mars are very low. The average temperature on Mars is about minus 80 degrees Fahrenheit. That's a mistake there. I need to correct that. It's about minus 60 C, okay, minus 80 Fahrenheit. So that's the average temperature on Mars. Temperatures can even get colder, minus 225 Fahrenheit at the poles. It's incredibly cold, okay? So Mars is a very cold and dry place. If that doesn't kill you, well, then you have the dust. The dust presents a choking hazard for at least 3 reasons. One, it's extremely fine-grained, okay, and so it's going to lodge itself into the pores of your lungs, just like miner's disease would affect the lungs of miners, okay, silicosis. So the dust in the coal mines is so fine-grained that it essentially goes into your lungs and it alters the performance of your lungs. Second, it's actually chemically toxic because this dust is made mostly of peroxides and perchlorates, which perchlorates are used on Earth as rocket fuel in different forms. Peroxides, imagine hydrogen peroxide in solid state, okay? That's really nasty. You put that in a bit of open wound and it's going to fizz, right? So that's what you would be ingesting if you ingested Martian dust. And then the third thing is that these dust grains themselves are very abrasive. They're likely to be relatively sharp, like glass shards from volcanic rocks. And they will also tear up the tissue that they come in contact with. So breathing Martian dust is really not something that you can do. You can already see that the movie The Martian had several issues, and of course the novel as well. Andy Weir, the author, actually is a good friend, so I'll tread lightly. But, and he's fully aware of this anyway. But for example, you cannot be blown away by a dust storm on Mars and howling winds on Mars because the atmospheric density, the air pressure is so low that even with hurricane speed winds, you would hardly feel a breeze. It's a bit like being exposed to the jet stream at high altitude in the stratosphere. You would hardly feel a breeze, even though the winds are traveling very fast, okay? So the Martian dust storm at the surface cannot blow you off because you would feel no pressure whatsoever, actually. It's enough to raise dust, to create a dust storm, but not to push you over, or satellite dish or anything like that. The second thing is that you will not bring Martian soil into your cabin to grow potatoes because this Martian dust is toxic. And so you're going to be breathing that stuff in, and that's really going to be nasty, okay? The potatoes themselves will also be contaminated with the peroxides, and that's really bad news too. Okay, so finally, you have radiation zapping. And by the way, I'm dwelling on this slide because after that we're going to be done with sort of the academic lecture. But you're going to be zapped by space radiation on Mars too. Radiation coming from deep space, radiation coming from the sun. Even though Mars has an atmosphere, it's not shielding you that much. And so you're going to be exposed to space radiation on Mars. And that over time will cause leukemia, skin cancer as well, and eventually death if you weren't dead from the other things. So we've landed successfully in 7 locations on Mars. They were all United States successes. Other nations have tried. They have all failed. Nobody has successfully landed on Mars except the United States. And the first mission that landed successfully was the Viking-Lander 1. And it found sand and a few rocks. A few months later, Viking-Lander 2, which was also traveling together with Viking-Lander 1, landed in this location where it found a lot of rocks and less sand. Okay? None of these places revealed the presence of life. There were life-seeking experiments on board these robotic spacecraft. There's a bit of controversy as to what activity they identified. It turns out in retrospect that what some of these life-detecting instruments detected was this very active chemistry associated with oxides, superoxides, and perchlorates, not life. Okay. Then there was a big lull of about 20 years, from 1977 to 1997. Okay, and the United States landed Mars Pathfinder. Mars Pathfinder was also a fixed spacecraft. It took this panorama, but it deployed a little skateboard-sized rover called Sojourner. You can see Sojourner here, driving up to that rock. Now, over time, the mothership, Mars Pathfinder, had its solar panels coated with dust because it wasn't moving, and so it lost power eventually. But the little rover had its own solar panel, and it was bobbing around amongst rocks and shaking off its dust. And so, for all we know, Sojourner is still roaming around on Mars, minding its own business, running through its program, which was to drive forward, sniff at a rock, reverse, go left or right randomly, and keep going until the next rock. Okay. So I was wondering if this was urban myth or not. I spoke with the chief engineer who was in charge of that program, and he explained to me that, well, actually, once Sojourner would have lost contact with the mothership, it would have switched to find the mothership mode. And so it would have essentially tried to ping from the transponder of the mothership, and it would have located the mothership and probably just kept on circling around and circling around. So what we expect to find, actually, is Sojourner deep in some sort of a moat that it would have dug itself into by driving around mothership. Okay. All right. So then, in 2004, we landed 2 rovers, Spirit and Opportunity, sand and dust. A lot of sand. Spirit actually got stuck in sand the first. And when that happened, that was a big scare. This was the first time we had real serious rovers on Mars. They were the size of a shopping cart. And Spirit got stuck in sand. So what do we do? So JPL convened a committee to study the problem. They used the engineering model of the Mars exploration rover in their backyard in a sandbox. They put the rover in that same predicament. They ran some tests, and then they found a solution. They wrote a 120-page report. They sent that to NASA headquarters. NASA headquarters is reluctant to just move ahead with this $800 million program without checking carefully, so it convenes another committee of people who review this report. They write a 50-page report that says, in a nutshell, this will probably work. Okay. So JPL is allowed to move forward with their plan. They load the command, they upload the command to the rover, and sure enough, it gets unstuck. And the gist of the command was, put it in reverse and gun it. Your tax dollars at work. All right, so Opportunity landed in a very interesting place too, and it's still working. Opportunity is still working. So now it's been on Mars close to 12 years, and it's still ticking along. It's visiting impact craters, and it's doing a good job at that. And then in 2008, somewhere in between, Phoenix landed near the North Pole of Mars, but still on exposed ground, not ice-covered ice caps. And it actually made an important discovery. It's Phoenix that, for the first time, determined that this Martian dust was made of perchlorates, the thing that we were mentioning earlier. That came from Phoenix. All right. It also revealed that if you land close enough to the North Pole or the South Pole, in this case, beyond 60 degrees north, all you need to do to find water ice is to scratch off the dirt from the surface, and you're sitting essentially on a huge sheet of dirty ice, okay, on Mars. Ice, water ice, okay. So that's, of course, a huge resource. It's an amazing discovery. Phoenix did that. Now, Curiosity landed in 2012. It's still roaming around. It actually is going up a hill to study the various layers that are exposed as it goes up this hill, but its tires are getting shredded by the sharp rocks at the site, so people are taking it easy with this. Notice that it doesn't have solar panels anymore. Curiosity is about the size of an SUV. All right, so now you're talking about a bigger vehicle, and it could not be just solar powered. You would need too much area of solar panels. So it's actually nuclear powered. It has a set of nuclear radioisotopic generators at the back. This is a selfie taken by Curiosity. All right, so what's a human mission to Mars? End of part one. Well, it's the idea of sending a small group of humans on a 2 to 3 year journey from Florida to a lethal frozen desert planet 1,000 times farther than the moon, have them be productive explorers, and optionally bring them back safely to the Earth. Okay, that's what a human mission to Mars. If you're an engineer, these are the requirements. Okay, so why would we do this? Well, this is my favorite reason, but I'll show you soon that there are many more. It's the tree of life. This is the tree of life on Earth. And what this tree represents is a mapping of all the forms of life that we're aware of based on our DNA. The closer we are on this tree with something else, the more DNA we have in common, essentially. Now, technically, it's not DNA here. It's 16S RNA, if you are a purist, but it's sort of the same idea. It's a tree that maps your genetic similarity. Okay, so notice, first of all, that we share some part in common in our DNA with all forms of life on Earth. There's no exception. Okay? Less with the forms of life that seem to be more primitive or different or distant, but more for the forms of life that we're more familiar with, in particular the mammals. And the tree of life on Earth is divided in 3 domains. The archaea and the bacteria are all microbes. The eukarya gather all the more complex organisms, all the way from simple cellular organisms that have a nucleus in their cell, to multicellular organisms, to ourselves. Okay, and so you, me, my dog, the squirrels and the trees outside, we're all eukarya. That's a piece of news. And what we're trying to assess is whether or not we could somehow be coming from a common ancestor whose existence is elusive at this point. It would have appeared early in life, in Earth's history. There are no rocks that are so old and so well preserved that would preserve a fossil of this microbe anymore. And if it's the case that we all come from this single organism that evolved over time into these different forms of life, well then we have to find another example of a tree of life on a different planet. So the idea of going to Mars is not just to find life. What you want to do is to find alien life. Okay? Alien life would be a form of life that somehow does not map onto this tree. It may not have DNA, or it could have DNA that has nothing in common with our DNA. It's something that would be the definition of an alien form of life. It could be that you go to Mars and you're going to find a microbe that actually maps onto this tree. It could be that life on Mars is actually related to life on Earth. That's a possibility. That's one possible outcome. And the reason why we think that's possible is because we have right now on Earth meteorites that have come from Mars. This is one of about 100 meteorites that we know of have come from Mars with certainty. And there are a few things in science that are certain, and I usually use this word very sparingly myself, but it's an amazing set of evidence that tells us that these meteorites have come specifically from Mars and not some other planet in the solar system, okay, or an asteroid. And so we know that planets are exchanging material naturally. How did this rock come here? Well, Mars gets hit every now and then by asteroids and comets. The big ones will splash rocks into space. These rocks will just travel and drift around. Most of them are lost forever. But some will run into the Earth, and they fall as meteorites. We collect them, and sure enough, hey, this one comes from Mars. Most meteorites that we have come from asteroids. There are many out there. They're always in collision. Martian meteorites are rare. About 1 in 10,000 meteorites, about 1 in 1,000 meteorites is a Martian meteorite. But here's the important conclusion, though, is that planets are not isolated. Okay? The Earth itself was hit by asteroids and comets. Earth rocks could have traveled as a result of the big impacts all the way to Mars. Microbes could have traveled inside these rocks and seeded Mars. And so if you find life on Mars, it could just be our distant cousins. Okay? Life, conversely, could have started on Mars and seeded the Earth. So all of these are possibilities, but the point here is that just finding life on Mars is not sufficient. For you to know that you have found an alien form of life, you would need to determine that it's not part of our tree of life. Okay? And that's a big question. We don't know if that exists. We don't know if that's possible. So this is what we're after, a big question mark as to our origin and the notion that we're looking for a different tree of life on Mars, something that would represent its own genesis, its own evolution. And maybe on Mars, the original form of life would be preserved because things are happening more sluggishly on Mars, not like the dynamic geology of the Earth. So where would you go to look for life on Mars? And in particular, where would you go for living life on Mars? Because for you to do DNA analysis, which is the only way for you to establish that the form of life is alien, you have to find a living form of that life. You have to do gene sequencing. And for that to be possible, you have to be finding living life. Okay. So where would you go look for living life on Mars? Well, these are the places where we've landed, and there are some sites of interest. But the point of this map is to tell you that Mars actually presents us with a large real estate. The planet is about equal in area to all the continents of the Earth put together if you took away the oceans of the Earth. Okay. So there's a large landmass here on Mars. And where would you go to find a place that has the chance of providing a living form of life today on Mars? Well, one thing you need to know is that all forms of life on Earth require liquid water. And everywhere on Earth where there is clean liquid water, there is life in it. So there's a one-to-one connection when it comes to Earth life with liquid water. You, me, my dog, the plants, the squirrels, the lichen outside, we all need liquid water at some point. Even in deserts, plants are possible only if there is, every now and then, some liquid water for them to process. So this may be coming across as geocentric, but our search for life on Mars is going to start with places where there was once water or where there might still be water on Mars today. Okay? Sure, an alien form of life might not want water, might actually be averse to it, but let's start with something that we're familiar with, and then we'll expand the search if that doesn't yield anything. So we know that liquid water has flowed on Mars early in its history. Even the most ancient terrains on Mars have signs of dry riverbeds. We know that water has been gushing onto the surface, even in the middle part of Martian history. We know that even in recent times, water has flowed at the surface of Mars, and even today. There are gullies, now we realize, are being formed by liquid water seeping out of the ground. Now, let me caution everybody on this particular point. Okay? It's liquid water, but it's possible that it's liquid. In other words, it is liquid only because it's super, super salty. At the cold temperatures of Mars, you cannot just have liquid water, as in tap water, run down these slopes. For it to be liquid, even at the cold temperatures, at the minus 80 degrees Fahrenheit temperatures of Mars, okay, this water has to be super salty. And we're not talking about table salt here. We're talking about perchlorates. Okay? So you're talking about a sludge of toxic salts, perchlorates, streaming down every now and then some of these canyon walls. And perchlorates are able to lower the freezing temperature of water down to minus 70 degrees Fahrenheit. Okay? So at the average temperature of Mars, it would be solid, but when Mars gets a little bit warmer than average, you can get some of these liquid brines. So nevertheless, it's interesting because it tells you that some of these gullies are forming today, and who knows, there might be forms of life that are able to take advantage of this liquid phase. Some life forms on Earth like perchlorates, okay, not at the concentrations that are needed for these brines, but it's amazing what some of these extremophiles, these forms of life that like extreme environments, are capable of coping with. So another thing you want to look for on Mars are places that are warm so that you have a chance of finding liquid water near the surface. The volcanoes are probably one of the best places to go search for liquid water underground. Here you have my favorite volcano on Mars. It's Olympus Mons. You can see it in profile here at the bottom compared to Mount Everest. That little black triangle is Mount Everest, okay? Olympus Mons is this gigantic shield volcano. Looks like a Roman shield or Greek shield, a Trojan shield. It's a volcano that is similar in type to the volcanoes we have in Hawaii, okay? They are shield volcanoes like Mauna Loa, Mauna Kea. Right, so this is Olympus Mons. If you're standing at the summit of Olympus Mons, okay, you're pretty much standing above the entire Martian atmosphere, which is thin to begin with. You're standing in space. You can close your eyelids. You would see sparks. That's cosmic rays hitting your retina. Time to head down. Okay, now these volcanoes are fascinating. With high-resolution imaging now from orbit, we're able to see things like lava tube entrances and caves on the flanks of these volcanoes. If you've had a chance to go to Hawaii, you'll know what we're talking about. If you haven't, you should really go. This is an example of a cave entrance on the flanks of one of the volcanoes on Mars. And to me, this is really mesmerizing because, you know, who knows what's going on deeper down in the lukewarm interior of these volcanoes. Maybe there's water dripping. Maybe there are bacteria that are coating the walls. Could be fascinating to explore. And then deeper down, pretty much throughout the planet, we expect to find liquid water beyond a depth of about 2 to 5 kilometers, depending on where you are. And the big question then is, will we be one day able to reach these depths by drilling? And would we find life in the liquid water that is at depth? We know on Earth that even at 2 to 3 kilometers of depth or 5 kilometers, there is still life, okay, where there's liquid water. Okay, it's incredible. And then there are the canyons. The canyons are very exciting, not only because they expose a lot of geology along their walls, but they take you that much closer to liquid water at depth. You don't have to drill through that whole section. A natural cut, if you will, is already made for you in the crust of Mars. So a good place to start drilling to reach deep liquid water would be the floors of these canyons on Mars. You're looking here at about 4 miles of height between the floor of the canyon and the top, okay, the top rim. So why would we go to Mars? I've talked to you about the search for life, but that's a scientific reason. Here's a comprehensive list, which I don't expect you to be able to read, but I'll read off a few for you, of why we might consider going to Mars. And the point of this list is this. Everybody has their pet peeve. Everybody has their notion of why we would want to go to Mars. It's possibly for science, for exploration, for the journey itself, for adventure, to look back at the Earth, to save the Earth, for the human experience, for education, for jobs, for national prestige, for national security, for technological leadership, for executive legacy, for international cooperation. We want to go to Mars because we should cooperate together. That's sort of often said. For resources, for commerce, for spin-offs. We want to go to Mars because we need more Teflon. Okay, to store waste. Migration, colonization, space settlement. This is sort of lumped together. People who want to move to Mars. To start a new branch of human civilization. That's sometimes brought up. To become a multi-planet species. That's Elon Musk's vibe. That's what gets him going. That's how he describes his motivation to go to Mars. It's to become a multi-planet species. We don't want to leave the Earth behind. We want to occupy more than one planet to have our eggs in more than one basket. Human destiny. Human destiny is an interesting one. You often hear, it's our destiny to explore. It's our destiny to go to space. It's our destiny to go to Mars. And the truth is, that's almost not distinguishable from religious faith, because who says it's our human destiny to go to Mars? Who says it's our human destiny to go into space? We really don't know. And can you possibly walk up to a congressperson and say, hey, please commit $400 billion of taxpayer money to going to Mars because I believe it's human destiny? It's a difficult argument to make because it's not written. So nowhere is it written that it's our destiny to go to Mars. Because we need the challenge. These are now quotes. Because we've already been to the moon. Because the Chinese are going. Because the Europeans are trying. Because it is there. That's what Mallory said of Mount Everest. Why climb Mount Everest? Because it is there. Because it is clean. That's what Mawson, famous Australian Antarctic explorer, said of Antarctica. I like to go to Antarctica because it is clean. Because it'd be cool, said an anonymous school kid. Why not, said JFK and Bobby Kennedy, on going to the moon and doing the other things. I've always wondered what the other things were. But, to boldly go, said Captain Kirk. Okay. And then, since this list is so comprehensive, I offer $1 to each person who comes up with a reasonable reason to go to Mars that is still not captured in this list. So I gave this talk not too long ago in Australia, and a hand came up and said, hey, what about this one? Establish a new colony of prisoners and convicts. Okay. So, but the bottom line is this, okay? You have to look at the history of exploration and why we explore, okay? We never do that to satisfy scientific curiosity. Let me repeat that one more time. The greatest expeditions in history were never done to satisfy scientific curiosity or anything as noble as that, okay? It was always to beat the competition, okay, or to get an edge. So, James Cook was not sent to the South Pacific because the British Navy was interested in botany. It's because the French were sailing those waters. JFK did not send Americans to the moon because somehow in the mid-60s we were interested in moon rocks. Okay? No, it's because the Soviet Union was a real threat, and we had to do something in space that was going to be beyond their possible reach. Okay, the Soviet Union at the time had sent the first satellite in space, the first living being in space, the dog Laika, the first human being in space, Yuri Gagarin, the first woman in space, Valentina Tereshkova. They did the first, and they were poised to do other things, the first spacewalk, Alexei Leonov, the first rendezvous in space. Okay, enough was enough. And so the president basically, even though some of these events had not happened yet, they were lined up. And so the president asked his task force, what could we do in space that we could beat the Russians at? And the answer, Mr. President, is to put a man on the moon and return him safely by the end of the decade. That's something that the Soviets could do, but we have a chance of beating them at that. It's far enough in the future, hard enough to do, that they're not going to get around to doing that immediately. And so that was the big bet. And President Kennedy, in 1961, stood before Congress, with the entire experience in human spaceflight in the United States being Alan Shepard's 15 minutes of suborbital flight. That's all we had done in space at the time. Okay. President Kennedy stood before Congress and said, I'm committing this nation to put a man on the moon and returning him safely by the end of the decade. And that was just an incredible thing to commit to and to say, even if you actually believed in it. It was really bold. Okay. So, but the point was, it served the national interest. It wasn't about science. It wasn't about moon rocks. Science is what you do once you get there. It's what dominates the activity that you conduct on the moon. Just like you take Charles Darwin on the expedition of the Beagle, or you take botanists on James Cook's expedition. Okay? Science is what you do once you are roaming those waters, but it's not the reason why you go there. The reason why you go there is to satisfy national interest. And so similarly, President Jefferson sent Lewis and Clark at great cost in those days. That was the Apollo program of their time, out west to figure out who was living out there, what routes were navigable. All of this exploration was done for national interest, not for science, really. So we haven't been to Mars yet because it doesn't seem to have served our national interest to rush to Mars quite yet. Okay, that's essentially it. And my argument is that it actually should. It actually should. We would be better off, and we would be better off as a leading nation in space if we actually led the first human mission and the first human settlement on Mars. And here's one of the reasons why. This is a chart. It's the only chart I'm going to show you. Okay, so bear with me, please. This is, at the bottom, the years from the past century, from 1920 to 1999, say the year 2000. And in the vertical column, the number of graduate degrees awarded in the United States, masters and PhDs. Okay. And you're tracking 4 scientific fields: math and computer sciences, engineering, physical sciences, earth and atmospheric and ocean sciences. Okay. We're not covering medicine, we're not covering biology there, but these sciences. And you can see that all of these lines increase towards the right. That general trend, of course, is due to population growth in the United States. Okay, the more people there are, more people go to school. People go to school, more degrees are awarded. So that's the reason why you have this general trend. But notice this huge spike in physics and engineering in the mid-60s and early 70s. Okay? That's the Apollo program. That's what it did to the nation. It essentially doubled, almost doubled, it multiplied by, almost doubled the number of degrees awarded in these fields compared to if there had been no Apollo program, no drive to go to the moon, no excitement for young people to go into science and engineering. So that's a powerful draw, and it's the Apollo program that led to this generation of people who started Amazon.com. Jeff Bezos will refer to the Apollo program as the motivation behind his enterprise. Elon Musk was inspired by the Apollo program, even though he was too young to really live it directly. So the point was, this was an incredible motivation for young people to go into science and technology at the time. And that is of huge benefit to a nation that cares about having a long-term future and a foundation in science and technology. So recently, China has landed a robot rover on the moon. And we actually never did that, but we could have done that. And Russians did that 50 years ago. And the Chinese are planning to land a human on the moon maybe a decade from now. And when that happens, we might also poo-poo that because it will be about 50 to 60 years after we've done it. But we would be missing the point if we mock those efforts, because what's happening is that as we speak, there's this huge wave of interest in science and technology among young people in China who are enthralled by their space program, who are really excited by the possibility of actually going to Mars beyond going to the moon, and who are going into science, engineering, technology, and studying math, okay, the STEM fields. And so this represents a real challenge for our descendants, our offspring, because you have a tidal wave there of people out there who are going to be going into the sciences. So this is why if we led a human mission to Mars, it would be an incredible incentive, it would be an incredible motivation for young people to get excited about space exploration again. And I think that would happen in a way that going to asteroids or going to the moon would not quite do. So how will we go to Mars? Well, we need a big rocket. So here's the giant rocket that is being built right now in Alabama. The first launch is scheduled for 2018. You have nothing better to do. I recommend you go to the Cape. It's going to be an amazing launch. It's the most powerful rocket ever launched when it does fly. Okay. And you can see here on the right, the space shuttle is standing next to the Saturn V rocket that went to the moon. We just needed one of those to go to the moon. The new rocket is being built in 2 versions. The smaller version just to get the crew up to space, and the bigger version to carry cargo into space, including spacecraft elements to go on to Mars after that. So here's a scenario to go to Mars. You will need 6 of these giant rockets, plus one of the smaller giant rockets, to pull off one mission to Mars. And a scenario would go this way. You first launch 4 of these giant rockets. These are cargo rockets. They put into low Earth orbit the elements of 2 spaceships. These spaceships have nobody on board. They just carry cargo, stuff that you don't have to travel with, but that you will need only once you get to Mars, like the house you will live in on Mars, or the rovers that you will drive on Mars. You don't need to travel with those things, so you're going to send these things ahead of time and make sure, in fact, that they land all in the same place on Mars and are in good shape and are waiting for you. Okay? Because you don't want to travel with this and then realize that, hey, the rover didn't make it. Well, all right. Okay. So 2 years at least before you go to Mars yourself, you send 2 cargo ships at the cost of 4 rockets to Mars, and they set up shop robotically on Mars. Then 2 more giant rockets are launched to put together your spaceship. Here it is. It's got nuclear rockets at the back. This giant marshmallow at the front is a inflatable habitat. It launches shrunken to fit in the rocket, but it expands by inflating. We can now build materials that are resistant to micrometeorites. So inflatables are even about to be tested on the space station. So this will be your habitat that you live in on your way to Mars and back from Mars. And then at the very front, the one capsule that will land you on Mars. Okay, that's the thing that's going to bring you to Mars. How you get off of Mars at the end will have been taken to Mars ahead of time. It's a little rocket launcher with another cabin on it. Okay. Now, once the spaceship has been put together in low Earth orbit, it's time for you to launch. So you and your, in this scenario, 6 other crew members, so it's a total crew of 7, you all cram into this giant rocket, a smaller version of it, and you dock with this thing in space in low Earth orbit, and you spend about a few weeks to check things out. And when you're ready, somebody presses the big red button, and off you go to Mars. So this is what the inside might look like. This is from my children's book, but it actually is constrained by some engineering. On the far left is the Orion capsule, the thing that will come back to the Earth at the end of the voyage and bring you to a splashdown or to a parachute landing on the ground with your entire crew of 7 people at the very end of your trip, okay? So the cabin at the far left will serve as the control center of the entire spacecraft, since it's going to last the entire duration of the mission. The service module is where you recycle water, where you recycle oxygen. This inflatable habitat is where you spend most of your time living. And then the Mars lander is shown here at the far right. Now, I don't have time to go into a lot of details, but I just want to comment on these sandbags that you're seeing lining the walls of this inflatable habitat. They're not sandbags. They contain water and food. And the reason why you want to surround yourself with water and food is because both water and food contain hydrogen. And hydrogen is a very good absorber of space radiation. It's a very good dampener of space radiation. Okay? So that's a good idea. You just protect yourself from space radiation. This is the normal run-of-the-mill, day-to-day space radiation that you get in space. If there's a solar storm which imparts, even sort of spikes the space radiation, well, then you all run into the lead-walled radiation shelter that's at the very center. And those things last a few days. You can walk out of it if you need to go fetch something, but you can cram in there for a few days and survive a solar storm. So that's the radiation shielding plan. Now, there's good news and bad news about this. The good news is this. If you drink the water, well, then you go to the bathroom, and there's a toilet, and your urine gets collected, and it goes into the service module. It gets recycled, purified, and it gets refilled. It refills one of the pouches of water on the walls of your spacecraft. So you don't take 2.5 years worth of water for 7 people on your trip to Mars. You take so much water, and then you plan on recycling it as you go. So a few weeks into your trip to Mars, you and your 6 crewmates are drinking each other's recycled sweat and urine. That's the good news. The bad news is what happens to food, okay? You're going to eat the food, and by the way, these pouches are labeled. You'll have your own set of pouches with your favorite foods, okay? But the outcome is still the same. You have to go to the bathroom. And now you can't recycle poop, all right? NASA is not even trying. It's extremely difficult to do. You need an entire biosphere to do that. We don't have the luxury of this. And so what are you going to do with the poop? You can't just open a window and toss it into space. For several reasons, no windows open in this spacecraft. But second, you don't want to pollute space. But that's not even the reason. The reason is that your poop still contains hydrogen. And you'd be throwing away radiation shielding if you got rid of your poop. So what you need to do is collect your poop very carefully in Ziploc bags, emphasis on lock. And those Ziploc bags go back on the wall where you took the food in the first place. Okay? And this is how it's going to work. So as you leave the Earth, you're surrounded mostly by fresh water and food. But by the time you come back from 2.5 years of trip to Mars, okay, you're surrounded mostly by recycled urine, several times recycled urine and sweat, plus everybody's 2.5 years worth of poop on the walls of your spacecraft. Okay. Now, we're all laughing. I think it's amusing too. Talk about an experiment that you would want to do with a real crew, okay, even in the basement in Moscow, to spice things up. But this is really what we will have to do. The reason why we don't do this on the space station is because the space station is in low Earth orbit, and even though it's outside the Earth's atmosphere, so it's somewhat more exposed to space radiation than we are on the Earth here, it's still within the Earth's magnetic field. And that is protecting the space station from a lot of nasty space radiation. So there's no need to surround yourself with water and food on the space station. But if we go into deep space, outside of the Earth's magnetic field, all of a sudden, you're going to be exposed to the brunt of space radiation. You really want to do something like this. All right, the big day arrives. You get to Mars. You cram the 7 of you in the cabin there, the Mars Lander, at the tip of your spacecraft, of your spaceship. You enter the Martian atmosphere. Parachutes deploy if you're lucky. You jettison the heat shield. You drop like a rock for a few seconds, and then the retro rockets come on, and you land. Now, at that point, you just hope that you've landed next to all that stuff that you sent to Mars 2.5 years ago, okay? Because if you didn't, well, let's see. So this is what you want to have landed next to, okay? Your habitat, and next to the habitat, there's even a pressurized rover, so that's like a motorhome. It's waiting for you. So if you land very close to this, great. You walk out, and that's your first spacewalk on Mars, and you walk into your new house on Mars. Hopefully you haven't forgotten the key or the code, and you enter. All right. Now, if you've landed a certain distance away that really precludes you from being able to make it on foot in your spacesuit, well then you can remotely control the rover, and this big shuttle rover can come pick you up. This is the airport shuttle scenario. Okay. Now, if you've landed too far from even the reach of this shuttle, of this rover, well, then you're toast. Okay, game over. All right. So here's what the inside might look like. I actually promised my publisher I wouldn't show every page of my children's book, but she's not here tonight, so. Okay. But this is what the inside looks like. And on the upper deck, you might have your sleeping quarters and the control center. There's a gradient in dirt from the top to the bottom. The clean rooms with the computers and the bedrooms at the top, still, for example, covered by the water tanks at the very top to absorb radiation from space. Okay? And then in the mid-decks, you have the lounge, the hospital area to take care of patients, the shower. And then at the bottom, the dirty, gritty deck, where you have the garage, the place where you repair your spacesuits, some of the fuel tanks that are now going to be used for storage. Okay. And then there's a connecting tunnel to your pressurized rover. Now, that's the scenario. In terms of turning this into reality, NASA has been going to different places on the Earth that are good analogs, similar in one way or another to Mars. This is a map of where these places are, and they're all extreme in one way or another. Okay? The Sahara is extremely vast and dry with sand dunes extensively. The Atacama is the driest desert on Earth, so it's extremely dry. The Arctic and Antarctica, where we go often, is extremely cold. The Australian outback is extremely red. Okay. Hawaii is extremely pleasant. Okay. No, Hawaii is interesting because of its geology. All right. So the place I'm going to talk to you a little bit about is Devon Island. It's in the Canadian Arctic. It's beyond the Arctic Circle. You can see the Arctic Circle there on that map on the lower left. And the red square is this map. So Devon Island is just west of the northern part of Greenland. And it's the largest uninhabited island on Earth. Okay. It's about the size of West Virginia. So like West Virginia, it's uninhabited, pretty much. Okay. And Devon Island, well, there's nothing wrong with that. Devon Island is interesting because it has also a large meteorite impact crater called Houghton Crater. It's a hole in the ground that formed 23 million years ago, 21 to 23. We're not quite sure yet. And the crater that it formed is much larger than Meteor Crater in Arizona. Meteor Crater in Arizona is about half a mile in size. Okay. Houghton Crater is 20 kilometers across. Okay, so about 15 miles across. So our project that has been taking us up to the Arctic every summer since 1997. So this coming year will be our 20th field campaign. It's called the Houghton Mars Project. So this is Houghton Crater, looking north from 10,000 feet of altitude. You can see the landscape is really barren. There are no trees that you can recognize. And it formed 21 to 23 million years ago. The Earth was warmer at the time. It was the Miocene, significantly warmer, I should add, than what global warming is predicting for us, to the point where not only were there evergreen trees in the Arctic at the time, but there were even leaf-bearing, deciduous trees, trees that would lose their leaves in the winter, like birch trees. Okay. Devon Island itself was already in the Arctic. Continental drift was happening, but 23 million years ago, it wasn't in the tropics or anything. It was already far north. Okay, so it's just the global climate on the Earth was quite a bit warmer at the time. And the Miocene is characterized by mammals roaming the land, and giant mammals in particular. So this is an illustration showing you some of these giant hares or rabbits of the Miocene. They were the size of greyhound dogs. And here you see them running away from a supersonic shock wave of an impact. Okay. So our campsite is off of the northwestern edge of the crater. You can see the edge of the crater is that dotted line. And you can see in yellow there our landing strip, and then the yellow dot with the circle in red, that's our base camp. Each square on this map is 1 kilometer on its side. We've been naming these features after things that we like or are our sponsors or potential sponsors. So we had a little pond at first called Google Earth Pond. That drew no attention. So we upped the ante. We named a hill Google Hill. Still no interest. So 2 summers ago, we named a large lake that you could not possibly miss on Google Earth, Google Earth Lake. And now we're talking. So, all right. But it's actually rare to find pieces of the Earth that are not named yet. And it's really an amazing experience to be asked to draw a map and designate places. And we have to designate them because we collect samples, we have to refer to these places as locations. You can't just give GPS coordinates and give them numbers. So it's actually a fun thing to do. So this is our camp. It stays up all year, even though it's occupied only in the summer. The airstrip over there. So now we're looking south. The crater's on the horizon. We have a little greenhouse that's set aside, but the other tents are about to be connected to the core. So each tent has a specific function, science tents, medical tents. In case you run a business, we're actually interested in considering you as because this is run privately by the Mars Institute and the SETI Institute. So NASA funds the research, but the camp actually is the largest privately operated polar research station in the world. So if you have a private business and you're interested in sponsoring scientific research like this, you are welcome to contact us, and we could get your logo on some of these tents, or name a module after you. Okay. The John Smith module for hazardous biology. Okay. That would be the latrine. Okay, then we have this greenhouse. It's the first robotic greenhouse in the world. It was able to reactivate itself at the end of the winter, and water growth trays with hydroponic plants growing. I want to tell you a few things about how we go to the bathroom. What you see on the left is the men's room. If you need to go for number one, you head towards this cluster of empty fuel drums. You step onto this cooler, step up to the occasion, and there's one fuel drum that's active there to collect urine, and there's a funnel actually to help you focus. So that's how you do it, and you just face the wilderness. You don't want to go to the bathroom just on the ground like this, in a place like this, because the ground actually in the Arctic at this location is very poor in nitrates and phosphates, which your urine is very rich in. And that, if you went to the bathroom on the ground, you would promote plant growth. You would terraform Devon Island. You don't want to do that. Okay? We want to keep it a polar desert that's Mars-like. And so we collect all our urine and we fly it out on empty planes that bring people or cargo in. And we dispose of it properly in the landfill on another island. On the right, you have an example of what happens when you enrich the soil in organics. This is an Arctic fox that might have died a few decades or hundreds of years ago, we don't know. But its organic remains seeped vertically into the ground. And now you can still see, a patch of moss growing where the body used to be, okay? And it mimics the shape of the body of the fox. So we know that this was a bad fox because it reincarnated into a form of life that was not as sophisticated. Okay. So we have polar bears as well to deal with, which is something you don't have to deal with on Mars. So there are two solutions for that, which we both use. We use both. One is to have dogs. We used to go to this guy who ran a rent-a-dog on a separate island. And so you can rent his dogs for the summer, and he would tell you you didn't even have to bring them back, which was really cruel. Of course, we always brought them back. And so these are our two polar bear guard dogs on threat condition alpha. Since we were not too confident that they would really spot a polar bear in time in this landscape, we also hire high school students from local villages, okay, who come with their shotguns and rifles. It's big hunting country over there. So this is a NASA project that's guarded by armed teenagers. All right, so this is what Devon Island looks like. It's an amazing place. It's what you call a polar desert. Sometimes when we go ask for funding for our project, we run into a congressman or congresswoman, and they will say, well, why don't you just go to Alaska? Why are we going to Canada for this? It's because Alaska is not polar desert. Alaska is cold, but it's tundra. It's just like Siberia. Siberia and Alaska are tundra. It's as cold as it gets. It's still very wet, very humid, plants everywhere, things grow. Polar desert is when it gets cold and dry, and you're really windswept and not friendly for any large form of life. And so you go to the Canadian Arctic, to the eastern part of the Canadian Arctic to find polar desert. So I'm not going to go into the geology in a lot of details, but I'm going to show you a quick set of slides where you have Mars on the left and Devon Island on the right, just to show you some of the comparisons we are able to study. Valley networks, we find amazing counterparts. canyons, gullies of type 1, gullies of type 2, gullies of type 3, sapping valleys, ground ice, and their amazing patterns of polygons, rock glaciers, lake beds. At the top is the site where Spirit landed. Right here on the floor of the crater on Devon Island, we have ancient lake beds as well. And if you wanted to walk away with some of the scientific findings of our project, I would say walk away with this one notion, which is that what we're finding is that most of these valleys and canyons that we see in ancient riverbeds on Devon Island, they were all formed under a very cold climate, oftentimes underneath ice caps and glaciers from the melting of the ice from the ground. And so this has forced us to actually propose a new interpretation for all these valley networks and canyons that we see on Mars. Maybe they don't imply at all that Mars was once wet and warm, like you often hear, that it had oceans and a warm climate in its past. Maybe Mars was pretty much always as cold as it is today. Okay. I won't go further into that, but that's actually, that has been an interesting idea and it's gaining traction. In spite of how cold and dry this place is, there are microbes. And sometimes in this landscape, you don't think that there is life, but actually it's teeming with life. It's hidden. It's living inside rocks and also underneath the surface. And here we have a rock that was sliced open, and right beneath the crust of the rock, you can see a rind of green. That's a colony of cyanobacteria living in the nooks and crannies of the rocks. Okay, so they're doing exactly what caveman and cavewoman used to do, which is to live inside caves, but not so far in that you lost the benefit of sunlight and warmth, but not so far out that you were actually exposed to the elements, okay, and to sunburn. You were in that twilight zone of your cave, and that's where you would dwell. Well, microbes do exactly that. They live inside the nooks and crannies of the rocks to shield themselves from the UV, the ultraviolet light, the wind, the dryness, but not so far in that they can't get sunlight anymore to photosynthesize. All right, so enough of the science of this place. I want to tell you how we're using this place to learn how to explore Mars. It's an amazing landscape, and you can play out all kinds of scenarios in your exploration adventure on Mars. I'm going to talk to you mainly about two things, rovers and spacesuits. Let's talk about spacesuits first. Here you have some pictures of our field tests of different kinds of spacesuits on Devon Island, and of course a picture to remember, to remind you of what the spacesuit used to look like on the moon. Incidentally, when we do spacesuit tests, we're doing these tests with the company that used to be called Hamilton Sundstrand. It's part of United Technologies. They were the contractors for NASA's Apollo spacesuit and also the Space Shuttle spacesuit and the Space Station spacesuit. So we have engineers who are working with us looking at what the future of a Mars spacesuit might look like. And as you'll see in a second, there's a big challenge. But the point of this slide is to show you that when we test a spacesuit, we often invite volunteers. So if you're a student on our project, a grad student studying geology, we might recruit you all of a sudden one afternoon to put on a spacesuit and go about your geology while wearing a spacesuit. So it's a very exciting opportunity for young people to be part of this. So here's the challenge of the spacesuit. This is the state-of-the-art Earth spacesuit. It's good for low Earth orbit when you're futzing around the space station or the space shuttle. It weighs on Earth 300 pounds. Okay, of course, you don't wear it on Earth, you don't need it. And when you're in low Earth orbit, you're weightless, so no problem. Okay. But if you took this spacesuit to the moon, it would have a felt weight of about 50 pounds. That's bearable. It's like a heavy backpack, but you can go about doing some geology with that. If you took the same spacesuit to Mars, you would have a felt weight of 125 pounds. Okay, you could not walk around on Mars with that spacesuit. In fact, you have to cut the mass of the spacesuit in half in order to have a spacesuit that would feel that it weighs only 60 pounds on Mars. And so the real spacesuit on Earth would have to weigh about 150 pounds, half of these 300 pounds. So that's a real challenge. We often say, well, going to Mars is just a matter of will. You know, we could go anytime. It's just politics. It's not. There are some real technological challenges to going to Mars. And one of them is to design a spacesuit that's lean enough to do the job. And so how do you cut the mass of something that's already lean and mean in half, all right? A spacesuit, you have to realize, is not just a piece of garment, it's a wearable spacecraft. So it has life support systems, computers, navigation systems, radios. It protects you from the low pressure, from micrometeorites, from the dust. It's an amazingly complex walking spacecraft. On top of that, you have to deal with things that you didn't have to deal with on the moon, like dust storms. Okay, so this is a dust storm about to run over a Mars base. So we are actually at NASA Ames putting some of these spacesuit fabrics to test. That's actually kind of fun. You sort of walk into a little dust storm made of Martian simulated dust. So that's mostly volcanic ash from Hawaii mixed with kitty litter. I'm not kidding you. It gives it more texture. All right. It's fluffier as well, so it allows it to be raised in the high gravity of the Earth. And you notice that these little grains of dust, when they hit the fabric of the spacesuit, this is viewed from a scanning electron microscope, it will actually ding the fabric. Okay, so over time, it would wear away at the current fabric that we use for spacesuits, so we have to come up with something better too. And then, of course, your spacesuit on Mars will have to allow you to do things like rock climbing, which, of course, we didn't get around to doing on the moon. So this is what the Mars spacesuit might look like. Okay. Sturdy boots, gaiters to protect your lower legs. It has a hard upper torso, like a rigid one, so that it's more resistant to wear and tear over time. The legs still have to be flexible, so you can't get around that. But you can replace the pair of legs. Notice there's a smartphone on your wrist. It serves as a digital checklist. You can also take selfies with it. And this is a rear entry suit. So you enter the spacesuit from the back. You open the backpack. It swings open like a refrigerator door. You climb in legs first. Your legs go all the way down to the boots. And then you insert the arms. And then you put your radio headset on. And then, actually, you put your radio headset on, and then you insert the arms. And then you close the door behind you, and you're now sealed inside your walking spacecraft. It's blue because it's the complementary color to Mars, to orange, which is a dominant color on Mars, so it's the color that presents the greatest contrast with the Martian landscape. On the moon, we had a rover, which, by the way, was not built by GM, but by Boeing. And I often ask, actually, when I show this picture, where is the Earth? Where's the sun? So most people can say, okay, it's to the left because the shadow is cast to the right. But where's the Earth in this picture? And it often is more puzzling. Well, it's actually indicated by where the antenna on the rover is pointed. Okay, that's not an umbrella, that's a dish, a satellite dish. And it's actually not looking at a satellite, it's looking at Houston. So it's overhead. And this means that they were roughly along the equator of the moon for this mission. So in any case, on the moon, we had one rover for 2 people. It was electric. They were forced to travel together, of course, when they were using the rover. But it served its purpose very well. It was very lightweight. And of course, you had to be wearing your spacesuit while you were driving this thing. So it was not pressurized. You didn't have a cabin to protect you. You had to rely on your life support in your spacesuit to survive driving around in this rover. Okay. Now, it was perfect. It did impose some very specific discipline. For example, you had to go to your farthest point at the beginning of your road trip so that in case you broke down, you still had your full complement of oxygen in your backpack to make your way back on foot and stay alive. So there were some strategies that were imposed like this. But generally, the way you want to explore is sort of meander your way out into the unknown and then drive back quickly. For Mars, because we're going to have much longer stays on the surface and more complex mission scenarios, and we'll need more flexibility in how we do surface operations, we anticipate having one personal ATV per astronaut. Okay, and so you will have one with your name on it, that's sized to fit your derriere. Okay, it's all-terrain vehicle ATV. Now, here's how it might work. So when you are riding on this ATV, you connect your backpack to a recharger of oxygen and also electricity. And so you have to travel with smaller batteries and smaller oxygen tanks, which is one important way to make your spacesuit much lighter. Okay? So all of a sudden, you and your rover have become a symbiotic buddy pair, okay, where you're offloading a lot of the mass of your spacesuit onto your little ATV. And then when you find something interesting, you unstrap, you unbuckle, you step off, and you go pick up a rock, and there you have it. Now this rover on top of that is robotic, and it's smart. In other words, you can talk to it, and it will follow you. So now you don't have to walk away and pick up a rock and bring it all the way back to the rover and waste oxygen. You just call it to you, or it just follows you automatically. And you just have to turn around and dump your rock into the trunk, and off you go again. Okay. Then, of course, you're still never alone. You have another real buddy on another rover. And in case one of these two rovers breaks down, no sweat. The other person, if that rover over there was broken down, the other person would just walk over to yours, get rid of that trunk on the back, which is just spare parts. And you have a rear-facing seat that you can sit on, and then you connect your backpack to the same source of oxygen and electricity again, and off you go. Right. So that's how you would do short distance exploration using ATVs on Mars. For longer trips, for a few days to possibly a few weeks, you want a pressurized rover. So that's your motorhome scenario. We're already testing different concepts for that. This is the NASA Johnson Space Center's Space Exploration Vehicle. It's actually a cabin that is put on this chassis, but you could put a different cabin if you wanted to on this chassis, or use this cabin as a design to explore asteroids without any wheels as well, so that it's a very versatile design. But this was an amazing thing, and I actually was lucky to be one of the first scientists to test pilot this thing in Arizona back in 2008. So this is what the inside looks like. It's touchscreen controls. You just joystick it. If you're right-handed, you sit on the right. If you're left-handed, you sit on the left. And to turn on the spot, you just twist the grip. To move forward, you push forward. To go in reverse, you pull back. And to turn, you just lean it sideways. It's very intuitive. The thing can drive at night, which is something we never did on the moon because the moon rotates extremely slowly, so we would always target a region where daylight was always constant. But on Mars, you're going to have this day-night cycle, which, by the way, the day on Mars lasts 24 hours and 37 minutes. I don't know about you, but I can use 37 minutes more each day. So to get things done. So I love this concept. You could be exploring, on day one somewhere in a spacesuit. At the end of your day, you climb back into your pressurized rover. You cook dinner, you write a report, or you pretend the comms are down, and then you go to bed. And then while you're sleeping, mission control, the robot or the rover in robotic mode drives you to the next spot. And in the morning, you wake up and, hey, you're at the edge of a canyon. It's a new day of exploration. It's going to be a lot of fun. The spacesuits are configured this way. You hang them on the outside of your rover so that you never walk into a habitable space with your gritty, dirty, dusty spacesuits. Remember, the dust is toxic. You don't want to bring that into the cabin where you live. So the spacesuits are docked backwards like this at the back, on the back wall of your rover. So you get into and out of your spacesuit directly from the inside of the rover by opening the backpack. There's a double door system. One door that seals the rover and stays with the rover at all times, and one door that is essentially the back of your backpack. Okay, so you open these double doors, you climb into your spacesuit from the inside or out, and off you go. So this is how it works. This is astronaut Rex Walheim, who was on the last space shuttle mission that flew. And he's demonstrating here how this works. So on his left there, you have a double door system. One of the doors is just the back of the backpack. The other is the door that seals the rover. He's climbing in legs first with a pull-up into the spacesuit, wearing his headset. And then that big bubble that you see next to his elbow, that's the visor of the spacesuit. And then the rings are where you insert your arms. Okay? And this pull-up is easy to do because, don't forget, you're in Martian gravity. So it doesn't take anything to do a pull-up and get yourself into a spacesuit. All right, so this is what it might look like conceptually. Bunk beds, and then a galley, and then the cockpit, and all the way in the back, the suit ports to get you into your spacesuit. The toilet is also at the back in the aisle, behind a red curtain for privacy. So we've been practicing living and operating in this kind of pressurized rover mode using simulating vehicles. So this is what we've been using, a military ambulance version of the Humvee on Devon Island. And notice that sometimes it's on tracks, not on wheels, to glide over soft ground. We were getting this one Humvee that we had often stuck, and so we requested from AM General, the maker of Humvees, a second donation. And they said, sure enough, we can do that. But for that, they had to pull a Humvee that was in Hollywood. This one actually served the first Gulf War and was recycled to become our NASA Mars 1 rover. But the second one, they pulled from Hollywood. And so this is the list of films where it's featured. And most famously, it's featured in The Rock. So when Sean Connery is taken out of prison by Nicolas Cage, I don't know if you remember The Rock, okay, and he's in a Humvee, and there's this conversation at the back of the vehicle with Nicolas Cage and Sean Connery. That's in our very Humvee. It is now on Devon Island. Okay. And so it was yanked from Hollywood, modified to our specs, and we actually got adventurous. We drove it to Devon Island most of the way, and it was epic. It's called the Ocarian because that's a longer story. I'll skip over that. But we drove the Northwest Passage actually to get it to Devon Island. And so a documentary film was made during the expedition, and it was just completed, and it should be coming out in movie theaters near you, we hope, sometime this year. So this is us along the Northwest Passage driving to Devon Island. Okay, so that's the movie. It's called Passage to Mars. And if you're not completely dead, at the very end, I'll have a 5-minute YouTube clip to show you if you want to see the trailer. But don't worry about staying if you can't. So when will we go to Mars? Well, the president had one space speech early in his first term in 2010. And the gist of it is that we're going to Mars, but by way of doing some intermediate steps, we're going to go to an asteroid first, and then by the mid-2030s, we'll go to Mars orbit, which I think is a good idea, to go to Mars orbit first, and then eventually to land on Mars. And so the schedule was presented, actually, mid-2030s, that's 2035, to get to Mars orbit. NASA has been quietly aiming for that ever since the speech. And so far, as we can tell, we're still realistically on target, although more funding would be needed really to give it more margin. And then landing on Mars could follow, and I expect to be around to see it. So if the president lives till about 80, then that would happen in the early 40s, mid-40s, okay, 2040s. So going to an asteroid actually is interesting, and I actually am in favor of it, although I hope it's done in a way that really keeps us focused on Mars and not gets us sidetracked in a big program to get humans to asteroids somehow. Asteroids are very interesting, and there's a great diversity of them out there. This is an example of a small near-Earth asteroid that was explored by a Japanese spacecraft. What I put next to it is not the Japanese spacecraft, that's the International Space Station for scale, okay? And so just to show you how small, at the same time gigantic, some of these things are compared to our structures in space. So this is asteroid Itokawa that was explored by the Japanese spacecraft Hayabusa. Now, the reason why exploring asteroids is relevant to going to Mars is because Mars has two moons, two little moons. They might be captured asteroids. They are irregular shaped, small bodies. One's called Phobos, and the other one is quite a bit smaller, and it's called Deimos. So Phobos is fear, as indicated earlier, and Deimos, dread or terror. And the 2-kilometer scale bar gives you a sense of the scale. Phobos is about the length of Manhattan Island. Okay? So if there were skyscrapers on Phobos, you could actually see them there on this picture. That's something I got to do, actually. I got to put some skyscrapers on there. So exploring Phobos would be extraordinary. The gravity on these small worlds is so low. On Phobos, the gravity is 1,700 times lower than on the Earth. So if you just push yourself on your legs on Phobos, okay, you would rise to about a mile. It would take minutes, and then you would slowly fall back from that height, okay? And by the time you hit the ground again, it would not be harder than how you launched yourself in the first place. So it would be an extraordinary experience to do that kind of thing. But to actually get around in this low-gravity environment, you might consider having a jetpack, okay? So we might resuscitate the MMU, the Manned Maneuvering Unit, that the early shuttle missions used back in the early 80s. Now, from Phobos, Phobos is so close to Mars that you would have a glorious view of Mars. Mars would be 6,400 times larger in the sky of Phobos than the moon is in our sky. Okay? So it'd be a spectacular giant blob occupying the bulk of your sky if you're on the right side of Phobos. All right. And then in the 2040s, first humans on Mars, and it's likely to be relatively simple at first, but then it eventually will expand into a base. Now, something historic happened just before the end of the year, last year. So in other words, just a few weeks ago. NASA convened the very first conference or workshop to propose the first human landing site on Mars. That's really historic because that's what we did when we went to the moon as well. We started having meetings to discuss where we would go and land on the moon. That's when it really got real, okay, because now you're planning something specific like traverses, and the astronaut will go here and pick up rocks there. And so you're planning something very specific. Well, we had that just a few weeks ago, the very first human Mars landing site workshop. And about 40 sites were proposed. There's an online website that has been proposed. I recommend you go check it out. I led a team actually that proposed this site. It's on the western end of Valles Marina. There's this canyon system on Mars, and shows you how long the canyon system is. It's huge compared to the United States that's outlined there in the background. Okay, so the landing site we're proposing is Noctis Landing. Just to give you an example, we're not pushing this particular one. I mean, I am, but I'm not trying to convince you. I'm just saying it's an example in this case of what the workshop considered. And so there you go. It's on the floor of the canyon. It buys you quite a bit of distance when it comes to eventually deep drilling on Mars and getting to liquid water. But at the same time, it's very near lots of interesting stuff, like the canyon walls for ancient geology studies, a giant crater to the south, Udamans, and then the Tharsis volcanoes that are within driving distance, about 2 weeks away from your base on Tharsis. So this is what your base might look like, sort of an international space station on the ground with a drilling rig. We might use plasma drilling, by the way, so it's a different technique from what's usually used in the oil industry. You just burn your way down, basically. Notice an airship. An airship would work. It could even have jet engines or rocket engines. The air is so thin. So who will go? We're getting to the end here. Who will go to Mars? Who will this lucky person be? Well, here are some things to consider. The crew size that we're considering, 5 to 8 people. Okay. Some will even suggest 4. I think that's really too few, in my view. But 5 to 8 is sort of probably in the correct ballpark. Beyond 8, you're looking at needing a bigger rocket, a lot more food. Every time you add a person, you have to consider that you're going to add 2.5 years worth of food for that person and all that extra bit of water to recycle as well. So it's a lot of overhead. What are the crew selection criteria? Do you want a gender mix, men and women? Do you want an ethnic mix? Do you want an international mix? Do you want a marital mix? You have 7 crew members, husband and wife, husband and spouse, husband and spouse, husband and spouse, and the 7th person. The homebreaker. Okay, so all of these 4 grayed out criteria are essentially arbitrary and somewhat political or societal in the sense that they're not there to make the crew really work better. You can imagine an all-male crew or an all-female crew be terrific, okay? It would depend on the people, of course, that you have traveling. You could imagine husband and wife couples working very well on a mission to Mars. I could easily imagine a complete disaster. Okay? Apparently you do too. International mix is something we probably have to live with because we cannot afford a mission to Mars on our own. Therefore we will have international partners sharing the cost and the complexity and the hardware. So like the space station is shared, we might have to go with international partners. That's actually, in my view, a plus. But oftentimes when you actually analyze it, it's actually an extra burden in some sense, or an extra consideration for the crew members to deal with, because you're dealing with somebody who has a different cultural background, different values sometimes. It's just not always easier to deal with than just somebody who's from your neighborhood that shares exactly the same values. Ethnic mix as well. Okay, but ultimately what you really want are Renaissance people and seasoned astronauts. And let me dwell on that for a quick second. Renaissance people, you only have 5 to 8 crew members. And meanwhile, you have many more skills than that to cover. Okay, you need people to fly the thing, so you need a pilot of sort. You need people to navigate. You need people to do medicine. You need a doctor who can do some surgery, who will also be a dentist. You want a biologist on board because you're looking for life on Mars, but you also want to do a geologist because you're seeing a lot of rocks. You want somebody who can repair the rovers, somebody who can repair the spacesuit, somebody who can repair the computers, a systems administrator, somebody who can repair the plumbing, the toilet, who's going to fix, this and that. So who's cooking? A lot of things. So what you're looking at is a crew of people who are highly specialized, because you don't want just jacks of all trades. You want aces of many trades within each crew member. And not only that, you want some redundancy. You don't want to have just one pilot. What if this person dies on that mission? Who's flying the ship? So you want people to have cross-training as well. So this means that every person on this crew will be multiply trained in several things and will be expert at several things. And that's actually not easy to achieve. And one of the things that makes it even plausible is time. Okay, for you to become an expert at several things, you need to be older. Yuri Gagarin, when he first went into space, all he had to do was press a few buttons and talk. He was 26 years old and he was a fighter pilot. Okay, he did a great job, but that was sufficient. But going to Mars is an entirely different story. You need to be really versed in all your spacecraft systems and your whole scientific agenda and everything. And so you're going to need people who are Renaissance people, people who will have had many more years of training. And no matter how smart you are when you're 26 years old, you just haven't had time to put 10,000 hours in all the different things you need to become an expert at, right? So therefore, a crew to Mars is likely to be filled with older people, people who are in their 50s, 60s, possibly early 70s. John Glenn went into space in his early 70s, okay? But of course, at the time, he was 70. Now, the 80s are the new 70s, okay? So, my point here is that the crew will be older. And older crew members are a good idea anyway, because when you're older, your cells divide more slowly. You're less prone to radiation damage, okay? That's important. And also you just, again, have had time to become an expert at different things. So a crew of 7 people, let's say, might have 6 people who are well above 50 to 55 years old, and maybe 1 token younger person who is there for mostly entertainment purposes, to pick on. Okay. All right. You want people to also film, videography, to record this. It's going to be, you need a lot of skills to do it right. Okay, so the crew member qualities, each person now should have a lot of knowledge, because at the end of the day, even if you don't get along with this person, if they can fly the ship and take you back to the Earth, well, that's what you really want. Okay? So knowledge, expertise, skills, experience. Number two, they have to be healthy, physically and mentally. Third, they really have to be motivated. And motivation is not just committing to 2.5 years of your life to going to Mars. It's committing to at least a decade or two of training before you get to go. And by the way, while you're training, you're not sure you'll ever go. So it really takes motivation to sign up. Then you have to be adaptable, tolerant of others, tolerant of change. Sometimes, I've been going to the Arctic and Antarctica for about 30 years, on 30 expeditions, pretty much. And you often have, every now and then, a participant who said, hey, this is really tough. I never signed up for this. I mean, I thought it would go this way. Well, no, you actually did sign up for this. You just didn't realize. Okay. The one thing that's a constant in expeditions is that they never go as planned. If you're doing anything new or original, it is not going to go as planned. If it goes as planned, you're not really pushing hard enough, really, is what it is. So you're not exploring, you're not going into the unknown. So you have to be adaptable. And then finally, you have to be altruistic. You have to be unselfish in your behavior. It's not about you. It's about your teammates. It's about your crew. It's about everybody else on Earth rooting for you. You have a major responsibility there. So you have to be altruistic and think of others before yourself. Okay, so beyond the first mission to Mars, this is when we come back from Mars. We might leave the place and not come back. That's certainly one possibility. People seem to be averse to this notion of going to Mars with just a flags and footprint mission. I don't think it's necessarily a bad idea. It could actually be an amazing boost, nevertheless, for our society to do something like that. And we would have done that, and we can move on to interstellar travel, other goals beyond that. But one idea is to actually settle on Mars, and then you might grow a base around your early settlement, your early little base. You might actually pressurize it under a dome. And then in the long term, some people are advocating, and I'm not among them, that you might terraform Mars. So you progressively transform the Martian environment, as if we knew how to do this properly, from a red Mars, which is what we have today, to a place that has a thicker atmosphere and is able to support simple forms of life that don't need a lot of oxygen, like lichens and mosses. That's green Mars, until we get to the stage where we have stable liquid water at the surface, where the atmosphere is thick enough, where the temperatures are warm enough, and we now have seas, ponds, oceans on Mars. Okay, so that would be the blue Mars. So Kim Stanley Robinson wrote a famous trilogy of science fiction novels called Red Mars, Green Mars, Blue Mars. So if you haven't read it, I'm sure it's in the library somewhere. But you have to bear in mind that these things don't happen overnight or from even one generation to the next. To get to the stage where you are greening Mars, it would take several centuries. The way you would do that, you have to warm up the polar caps, maybe by sprinkling soot on them so that they absorb more sunlight, release CO2, thicken the atmosphere, warm up the planet. That's a process that would take centuries to happen and stabilize. And then, to go beyond that, to continue doing that, it would take about 1,000 or several thousand years to get to blue Mars, okay? So you're talking about a huge expenditure in resources. Think taxpayer dollars, probably from the entire planet Earth, singularly focused from generation to the next, from one generation to the next, on somehow terraforming Mars. That's just extremely unlikely. Okay? We don't build cathedrals anymore, or pyramids, especially if we're in a democracy. So, I actually don't think that this is likely. Some people say that we will actually make faster progress in genetic engineering. We could create a human being that's better adapted at living on Mars almost the way it is than trying to change Mars into a place that we would like as we are. So this is the notion of creating Homo Martis. This is an actual naked person in a quarry in California, okay? But it's showing you what we mean by somebody who could survive on Mars the way it is. Right? But genetic engineering is making strides, and this is not completely out of the question. But in my view, it's no more far-fetched than the notion that you would transform Mars into an Earth-like place over the course of thousands of years. Okay? And then finally, maybe what, in my view, has the greatest hope of actually happening is that we will identify Earth-like planets around nearby stars and really make a push for interstellar travel in one form or another. And it could well be that this is a notion that somehow is now floating around quite a bit. The notion that we as biological beings, we are actually condemned to pretty much stay on planet Earth for the foreseeable future. And what we might send out there, including into interstellar space, are things that are robots. Robots that are so similar to ourselves in some sense that they become so attaching that they are essentially treated like they were human beings. It's a bit like the Data character in Star Trek. Okay, it's a robot. He doesn't have to wear a spacesuit when he goes out in space. He just goes in his uniform. He's a robot, but he has acquired the behavior and the traits of a human being, and we relate to that person as a person, as a member of our own society. Okay, so that could be the concept for the future, where we as our biological, with our biological dependence to the Earth, we're stuck here, but we could dispatch our avatars or our robots out into space. Okay. Anyway, just to give you a sense of the challenge, Pluto is at about 100 astronomical units from the Sun. So first of all, the Sun is to the far left. The scale bar goes in increments of times 10. So you see where the Earth is, it says 1. By the time you get to Saturn, you're actually 10 times farther away from the Sun than the Earth is, okay? So of course you couldn't show that. That's why it's compressed. But then by the time you get to the edge of the heliopause, which is where the Sun's influence stops, you are at about 100 times the Earth-Sun distance. Okay? And so Pluto is roughly in that neighborhood. And then there's the Oort cloud of comets, where, of course, it's still bound to the Sun gravitationally. And that extends all the way to about 100,000 astronomical units. And then you get to the nearest star, Alpha Centauri. Alpha Centauri is several thousand times farther away than Pluto. Okay, so there's a big gap. There's an abyss of space between the last body well, it's not even the last body, but some of these bodies out there that are at the edge of our solar system compared to reaching the next star. Okay. So it's going to take some breakthrough in space travel and physics to get us out there, or in biology to create beings that don't care about their longevity or their mortality anymore. Beyond that, we have the galaxy. So this is not our galaxy, obviously, because we are taking a picture of it. This is the nearest giant galaxy to us. It's the Andromeda galaxy. All right. So if you look in the right place in the night sky, you'll see the Andromeda galaxy with the naked eye. It's sort of a fuzzy patch. Our own galaxy, the Milky Way, is about like this. It has spiral arms. It's essentially a swarm of stars, and it contains, galaxies on average contain 100 billion stars. Okay, so that's 1 followed by 11 zeros. The Andromeda galaxy is similar to ours. It's 1 followed by 11 zeros of stars out there. And we know of about 100 billion galaxies in the universe. This is the next picture. A corner of space taken by the Hubble Space Telescope, deep field camera. So every one of these spots that you see most of them are not stars, they are galaxies. Okay? So each one of them a swarm of about 100 billion stars. And we're now discovering that all of these stars around us, not all of them, but 50% or more, have planets around them, several planets. Okay? So planets are not a rare phenomenon anymore. I mean, they never were, we just wondered. But now we know that they're common. And so if you do the math, okay, if each star has on average 10 planets or 10 planetary bodies, with 100 billion galaxies and 100 billion stars per galaxy, that's a 1 followed by 23 planets in the known universe. Okay. So that's close to a mole in chemistry. All right. It's a staggering number. It's actually more planets in the universe than there are sand grains in all the beaches of the Earth put together. You can do the math. We can come up, astronomers who have a lot of free time, like do back of the envelope calculations like this. Okay, you know the number of grains of sand that are in a cubic centimeter of sand, beach sand. You know how long a stretch of beach we have on the Earth. If you add up all the continental edges. You do the math, and you find that it's a number that's smaller than 10 to the 23. I didn't do it. So that's it. I have my little book. It's available. It's really for kids, but I found empirically that it's mostly adults buying it. And it's published by Scholastic. That's it. This is King Kong, my dog. Okay, good. All right. Okay, thank you so much.